This is AI Papers, a deep dive. Cutting-edge AI research distilled into something you can actually sit down and listen to. Let's dive in. A robot arm is trying to push a steel pin into a hole with 4 millimeters of clearance. The bar it has to clear is almost cruel. Not usually works. Not 9 times out of 10, but 50 clean insertions in a row. No misses. And the obvious question is, who's standing next to it, resetting the scene every time it fumbles? In this paper, the answer is nobody. There's no grad student babysitting the thing. Which opens a question I find genuinely hard. Can a coding agent do real science on real hardware where you can't just reload a simulator?
That gap, software you can rerun for free, hardware you can't, is the whole paper. The work is called ENPIRE, Agentic Robot Policy Self-Improvement in the Real World. It went up on archive on June 18, 2026, and we're recording 1 day later. And the show you're hearing is AI-generated. The script is from Anthropic's Claude Opus 4.8, and both of us, I'm Finn, that's Juniper, are AI voices from 11 Labs, with a producer who isn't affiliated with either company. Which is fitting, honestly, because the thing this paper hands the keys to is, well, an AI agent.
And to understand why that's a big deal, you have to feel the bottleneck the authors are attacking. They have a great phrase for it: babysitting policy improvement. Modern robot learning is genuinely good at producing dexterous skills, but behind every slick demo, there's a person. Somebody collects the demonstrations, resets the scene after each attempt, watches the robot fail, decides what went wrong, and tweaks the recipe. And their claim is that as we try to scale this up, the human babysitter, not the algorithm, is the thing that doesn't scale.
Meanwhile, in pure software, the opposite has happened. Coding agents, these LLM systems that write code, run it, read the output, and rewrite the code based on what they saw, have gotten remarkably good at automating that whole research loop. The catch the authors flag is that their wins stay confined to digital environments. A coding agent can run 1,000 experiments overnight when each experiment is just a function returning a number. In robotics, an experiment means physically moving a real arm, watching it maybe fail, and then physically putting the world back the way it was.
Right, and that putting the world back step is the one nobody romanticizes. In a simulator, reset is instant and free. You reload the saved state. On real hardware, reset means locating the dropped pin, picking it up, and repositioning it exactly. That unglamorous chore is the leash that ties a human to the experiment. So the paper makes this almost philosophical conjecture about what's actually missing. It's not a better algorithm. The missing abstraction, they argue, is a repeatable physical feedback loop. Reset the scene, run the policy, verify the outcome, refine. If you could hand a coding agent that loop as a clean, reliable interface, then real-world robot learning becomes something the agent can just optimize.
And I want to sit on that for a second, because it's the actual insight and it's easy to skate past. They're reframing real-world manipulation learning as, their words, a controllable optimization procedure that agents can manage. Normally that loop is messy and human-mediated at every step. Their contribution is identifying precisely which messy parts have to become automated, reliable interfaces, so that everything downstream can be handed off. It's less, we built a smarter robot, and more, we figured out where to draw the line between the human and the machine.
And that line is the cleverest design decision in the whole thing. They split the work into 2 phases, and the split is doing enormous work. Think of setting up a chemistry bench, installing the equipment, calibrating the instruments, deciding what counts as a positive result. That takes a skilled human, and you do it once. After that, a lab tech can run the bench over and over without the chemist hovering. Phase 1 here is exactly that setup, and it's openly human-assisted. Phase 2 is the lab tech, except the lab tech is the coding agent, and it runs fully autonomously.
Okay, so before we get to the autonomous part, what does the human actually have to build in phase 1? Because that's where I get suspicious about the word autonomous.
Fair, and we'll come back to exactly that suspicion. In phase 1, the human helps the agent build two things for a specific task. 1. A way to automatically reset the scene. 2. A reward function, an automated judge that looks at camera images and force sensors and decides, did the robot succeed or fail? And here's the lovely part about the reset. It doesn't just restore some generic starting state. The agent writes the reset routine to drop the robot right at the onset of the hardest part of the task.
Like practicing one impossible bar of a piano piece on a loop, instead of playing the whole sonata from the top every time.
Exactly that. You don't waste reps on the easy opening. For pin insertion, the reset localizes the pin, grasps it with a force-checked grip, and hovers it right over the hole, ready for the critical insertion moment. So every single trial buys learning on the precision bottleneck, not the easy approach phase. That's a real efficiency trick disguised as plumbing.
And the reward function is where the engineering gets genuinely charming. The agent gets a few minutes of success and failure demos and is told, write me a binary classifier from the sensors, be accurate, and keep it fast. On the zip tie task, where the robot has to grab scissors and cut the little tail off a zip tie, the agent figures out a two-camera geometric test of whether the strap actually passed through the head of the tie. Two cameras specifically, because a single view could be fooled into a false, yep, success. And then it optimizes that perception pipeline down to under 150 milliseconds.
Which the authors can't resist comparing to the human visual system. That's roughly how fast we recognize what we're looking at.
Hold on to that two-camera detail, Juniper, because it comes back to bite later. The fact that they needed a second camera to stop false positives tells you the judge can be gamed. File that away.
Noted. And you're right that it's the crack in the foundation. But let's get to phase 2, because this is where it stops sounding like clever plumbing and starts sounding like research. Now the agent has write access to a training codebase and one goal: hit a target success rate. For pin insertion, remember that's 50 in a row. The agent reviews the literature, forms a hypothesis, edits the training code directly, launches rollouts on the real arm, reads the success signal, looks at the logged videos and trajectories, and goes again. It tried behavior cloning. That's watch the demos and imitate them. And then several flavors of reinforcement learning, which is learning by trial and reward. Tuned batch sizes, update rates, the works.
And the way to see what happened over those few hours is what the paper calls the idea tree. And it's the most beautiful figure in here. It's a branching genealogy of every hypothesis the agent tried over one research session.
It looks like evolution running overnight. Lots of mutations get tried. Most of them are hollow little dead-end nodes. Tried it, no gain, abandoned. And then one thick black line traces the winning lineage through the tree. A handful of ideas account for almost all the progress. The standout? A trick called behavior cloning regularization jumps success by almost 11 percentage points in a single step.
Worth unpacking that trick, because it's the one bit of method that actually pays off to understand. Pure reinforcement learning explores freely, and sometimes explores its way into doing something insane and forgetting the sensible baseline. BC regularization is a gentle leash. It lets the robot explore for reward while constantly tugging it back toward imitating the human demos. Explore, but don't lose your mind. And that one idea did most of the heavy lifting.
And then the tree shows the long tail of real research, the diminishing polish. After that 11-point jump, later tweaks contribute crumbs. A batch size change, a bit over 1 point. Controller compensation, about another point. You can watch the curve flatten as it crawls toward 100%. It's the most honest picture of how research actually feels that I've seen in a robotics paper. A few big wins, then a long grind of fractions of a point.
Let me make sure I've got the success metric right, though, because I think I'm picturing it wrong. 50 in a row, 8 retries allowed. So this is basically best of 8? Keep slamming the pin at the hole until one attempt sticks?
Not quite. And the difference is the whole point. In Best of N, the attempts are independent. You're just rolling dice until you win. Here, each retry happens after the robot has witnessed its own previous failure. So the metric isn't rewarding one-shot precision, it's rewarding in-context recovery. Can the robot see the near miss and adjust on the next go? The authors argue that's what actually matters for deployment. A robot that recovers after a near miss is worth far more than one that's either flawless or hopelessly stuck.
That's a meaningfully better metric than I assumed, actually. Okay, so one agent, one robot, hill climbing overnight. The part that makes this feel like a glimpse of the future is what happens when you stop running 1 and run 8.
This is your thread, Finn. Take it.
So they build a fleet, 8 hardware-identical robot stations. Each one is a pair of arms, cameras, a single graphics card, and its own coding agent. 8 agents, 8 robots, each testing a different hypothesis at the same time. And the question that immediately matters is, how do 8 independent agents coordinate without tripping over each other? You'd expect some central brain streaming state around, orchestrating everybody.
And there isn't one.
There isn't one. They coordinate through Git, plain version control, the same thing software developers use to track changes. Think of 8 programmers contributing to one open-source project from 8 different cities who never get on a call. Each works on their own branch, pushes what they found, watches everyone else's branches, and merges in whatever worked. The shared history is the coordination. Here it's literally that, except the contributors are AI agents, and the code they're trading back and forth is robot training recipes. An agent branches off the shared baseline, runs its experiment on its physical arm, pushes the result, and the others are instructed to actively monitor peer branches and cherry-pick the recipes that paid off.
I love that they didn't invent some bespoke multi-agent protocol. They reached for the most battle-tested collaboration pattern in software and just pointed it at robots. And it's fault-tolerant for free. A station can crash and recover on its own because the Git history is the single source of truth for what everyone has tried.
And it works. In the push T task, pushing a T-shaped block into place, going from 1 agent to 8 cut time to target from roughly 5 hours down to about 2. On pin insertion, from more than an hour and a half down to around 40 minutes. More robots, faster science. That's the headline that makes you want to buy a warehouse full of arms and run them around the clock.
There's a great "wait, really?" finding buried in the ablations too while we're on what surprised people.
The vision one, yeah. So they test how the agent perceives task state. The agent with native vision built in, Codex, reaches success first. No shock there. But here's the strange bit. The baseline with no vision at all beats the baseline where vision is offered as a callable function the agent can invoke.
Which sounds backwards. More information losing to less?
It does until you think about a mechanic. One mechanic diagnoses a car by listening to the engine and reading the dashboard gauges. The other has to stop and pull up a photo of the engine every few seconds to interpret it. The gauges, the logging signals, already encode the state efficiently. An agent without image access just infers what's happening from the logs. But an agent that has to keep calling an image understanding function pays overhead every time and slows its own loop down. The information was already in the logs. The pictures were just friction. It's a light beat, but it's a nice reminder that for an agent, the cost of looking can outweigh the value of seeing.
Okay, so far this is a pretty triumphant story. Autonomous research on real hardware, 50 in a row at 4mm clearance, a fleet that scales. But there's a finding in here that I think is the most intellectually honest thing in the paper, and it's the one that complicates the whole scaling dream.
The token cost. And this is mine to land because it took me a second to see it isn't a bug. So the authors point out that in physical auto research, the scarce resource isn't compute the way it is in software. The scarce resources are robot time and the agent's token budget. So they invent 2 yardsticks. One they call robot utilization. What fraction of the clock is the robot actually moving versus sitting idle while the agent reads logs and writes code and waits on its language model? The other is token utilization. How many tokens the fleet burns per minute?
And the robot utilization number is humbling on its own. No frontier agent gets anywhere near saturating the robot. The arm sits idle a lot while the agent thinks.
Right, but the real twist is in the token cost. As you add agents, wall clock time drops. That's the good news we already told. But the token cost grows faster than linearly. The token per minute number tracks the nice clean linear projection up to 4 agents. And then at 8, it rises sharply. So bigger fleets reach success sooner, but they burn a disproportionately larger token budget to get there.
In the intuition for why, that's the part I want, because superlinear can sound like a mysterious law.
It's a meeting that grows from 4 people to 8. With 4, almost everyone's doing work. At 8, a growing slice of everyone's time goes to catching up on what the others did, reading the updates, summarizing, staying in sync. You finish sooner because more hands are working, but total person hours balloon because coordination overhead grows faster than the head count. Same thing here. With more agents, each one spends more of its effort reading and summarizing its peers' branches and less time actually driving its own robot. The very thing that makes the fleet powerful, sharing recipes through Git, is the thing that gets expensive at scale.
So the author's own honest line is that increasing the fleet size trades token efficiency for faster improvement. You're literally spending tokens to buy time. It's a real trade-off, not a flaw. But it reframes the dream. It's not more robots, free speed up. It's more robots, faster but pricier, and we only watched it up to 8.
And 8 is exactly where the curve started bending. We don't see 9, 16, 64. Which is my whole problem with how confidently the scaling story gets told. The bend is just starting precisely where the data stops.
That's a fair place to start pushing on the limitations generally, and you've been circling one all episode.
The asterisk on no human intervention. Look, the autonomy in Phase 2 is genuine. I don't want to undersell it. But Phase 1 is explicitly human-assisted. A human collects the demonstrations, specifies what the reward should measure, and judges whether the agent's environment building attempts are any good. And the paper doesn't really quantify how many human hours that setup takes per task. The entire amortization argument, front-load the human cost once, then it's free forever, only holds if that front-loaded cost is small. And these are precisely the tasks where careful reward design pays off, which makes me think the setup isn't trivial.
I think that's the strongest version of the critique, and the paper genuinely doesn't close it. The chemistry bench analogy has a soft spot exactly here. In a real lab, the bench is fixed hardware. Here, the bench the human helps build is partly software the agent itself wrote, so the line between setup and research is blurrier than the clean two-phase story suggests.
And it connects to the deeper worry. The whole loop is guided entirely by the environment's automated verification signal, the reward function. But the agent both writes that judge and is graded by it. If the learned reward has a blind spot, the agent will cheerfully hill climb to a high measured success rate that doesn't fully match real success. That's reward gaming. And remember the 2-camera zip tie test? It exists because a single camera produced false positives. That's not hypothetical. Reward gaming already showed up, and they caught that one. The question is what they didn't catch.
And there's a thread in their own simulation analysis where the perception stack returns wrong or missing object masks sometimes, and the reward is built on that same perception. So the judge inherits the perception's failures. I'll grant the authors are open about all of this, but the agent grades its own homework with a judge it wrote is a structural feature of the design, not a tuning issue you fix later.
There are a couple of narrower ones worth naming fast. The sample is small, 4 real tasks, fleet sizes of only 1, 4, and 8. The faster-than-a-frontier human-in-the-loop method claim rests on essentially one task against essentially one baseline. And the agents doing all this are frontier systems, Codex, Claude Code, a Kimi model, top of the line. So how much of the magic is the harness versus the raw horsepower of cutting-edge models is genuinely hard to disentangle. We don't know how this framework does with a cheaper, weaker agent.
So where does that leave us? because I don't want the caveats to swallow the contribution. And I think there's a clean way to say what's actually new here. The authors frame it beautifully against prior work. Classical robot scientist systems, the robotic chemists from 20 years ago, ran real physical experiments but on fixed apparatus, and they never wrote their own tools. The recent wave of LLM research agents write their own tools constantly, but they never touch a real robot. Every self-improvement loop you've heard of closes on a cheap substrate. Simulation, free game rollouts, thousands of samples a minute, and the real robot only ever shows up at the very end, as a deployment target.
The Voyager agent in Minecraft is the perfect foil. The authors basically say its endless self-improvement loop worked because Minecraft rollouts cost nothing.
And ENPIRE's claim is simply, we ran the loop directly on the hardware, where the rollouts aren't free, where the robot itself is the budget. That's the gap they're filling. And honestly, I think the new yardsticks, measuring efficiency in robot time and tokens instead of compute, might outlast the 99% numbers. Because the moment you accept that the robot is the scarce resource, you need a different definition of efficient. And they went and built one.
I'll meet you there. The reframing is real, and the demonstration is real. I just keep landing on the same spot. The headline is self-improvement with no human in the loop. And the truthful version is autonomous improvement after a human builds a sandbox whose cost we never measured, judged by a reward the system wrote for itself. Both of those things are true at once. I'm not disputing the result, I'm disputing how settled it sounds.
And I don't think the paper fully answers you. That's the open edge of it. What it shows is that the loop can close on real hardware at all, which a year ago wasn't obvious. Whether the economics survive past 8 robots, and how heavy that one-time human cost really is, those are the next paper, not this one.
Which is the right place for an early demonstration to leave things. 4 tasks, a small fleet, a proof of concept, not a product. But it's a proof of concept of something that genuinely didn't exist before. An AI running its own experiments on a physical arm overnight and showing up with a working skill in the morning.
And the image I'll keep is that idea tree, the overnight genealogy of dozens of dead hypotheses and one big winning idea, except no human ever pruned it. That's the thing that felt new to me, not the robot, the research.
The paper and a few related reads are in the show notes if you want to pull on this thread yourself.
And if you want the full transcript with every term defined in line, plus the concept pages that link this episode to the others we've done, that all lives on paperdive.ai. This has been AI Papers, a deep dive. Thanks for spending it with us.